Right, now we are recording. So, as I mentioned, the Canvas message I sent, on Thursday I will be at the Gulf Park campus teaching from there. If anyone comes here, it did not work so well it actually did not work at all last time to try to connect, but I have new information that will hopefully make that possible. So we'll see what happens. So for this entire week, Tuesday and Thursday, both, the subject is this numerical differentiation. So section 9.1, how we use values of a function at selected points to approximate its derivative or second derivative, or any order derivative. And we'll find out certain things that we've been using earlier in the course, such as Taylor series and Lagrange interpolation will be helpful for that. So today I'm going to talk about the Taylor series approach, and then on Thursday, Lagrange interpolation approach, and also sensitivity of the problem of numerical differentiation. As we've seen some examples, if you're doing a simple difference quotient to approximate a derivative, like f of x plus h minus f of x over h, and you choose h too small, then that actually causes a terribly inaccurate approximation due to floating point arithmetic issues. So that's something I will take a look at on Thursday also. Okay. So here's the problem that we're going to solve. So you give us a function f of x, and you can evaluate at whatever point, and then, or maybe at its values at selected points, and you have a point x naught that's given, and your goal is to approximate the derivative of at x naught. So we're not trying to, so this isn't like differentiation you're accustomed to from calculus, where you're given a formula for f of x and you come up with a formula for derivative using all differentiation rules like product rule, quotient rule, chain rule, etc. In fact, all those rules that you learned, we're not using them at all for this. We appeal to the definition, basically. Also, the simplest differentiation rule that we have, a power rule for polynomials, is helpful. And the thing is, when you're dealing with, when you're wanting computers to solve these kind of problems for you, you want software to compute a derivative for you. You can do it the way you're accustomed to from calculus. There's obvious software tools like Maple, Mathematica, and so forth that can do that, but that's not really efficient. This isn't. So symbolic differentiation routines are very effective, but they're not as efficient as what a computer does best: add, subtract, multiply, divide. A computer can get an approximate value of a derivative, like the high accuracy, right? Maybe order 10 to the minus 10 or something, a derivative at that point a whole lot faster than a package such as Mathematica can compute a formula for a derivative of a function, if it can do it. Some derivatives are really difficult to get, and then plug in the point x naught at which you want a derivative. That's a whole lot slower. The other thing is, do you even have f of x in the formula? There are a lot of cases where you don't have a formula for f of x. Maybe you just have a vector of values of f of x at selected points, and you need to try to approximate a derivative from that. So that's all you have. All those symbolic differentiation codes will not help you anyway. I actually have written code, like a long time ago, as an undergrad, to carry out symbolic differentiation. It's something I did just for fun. If you just do a straightforward application of differentiation rules you learn, like product rule, etc., that would work, but the expressions that you get are very inefficient because there's a lot that can be optimized. Like, for instance, if you differentiate something and you get 0 or 1, things like that. And it is possible to optimize those kinds of expressions, but that's very difficult to do in general. So everything that human beings do to work with expressions in an efficient manner, like simplifying, recognizing opportunities to simplify things, for recognizing which rule to use in a certain situation. It's not easy to get a computer to duplicate that thought process. So, and that's not the best use of computing resources anyway. That's why we focus on these numerical methods, and we're doing it this week for differentiation, and then in next few weeks we'll be doing the same for integration, which is a much more difficult problem. Okay, so really what's happening here is we are giving up some accuracy because we're only computing an approximation, but it's so much more efficient than the alternative. So the way this works is if we have values of our function f at equally spaced points, so at x0 itself and then x0 plus or minus jh, so spacing as an integer multiple of h, you can think of h as being like the delta x, then we can interpolate f by a polynomial that passes through these points, and then take a derivative of the polynomial exactly. Now, we will use that approach explicitly when we use Lagrange polynomials on Thursday, but the same idea is used, the one I'm going to show you today, where we use Taylor expansion, because in that case too, we are representing f by a polynomial. Okay. So I'll use an example to illustrate the process of constructing a numerical differentiation method. So the method that you use, the approximation you get, depends on which points you're using to approximate the derivative. So I want the derivative at some point x0, and I'm going to use these three values of f. So x0, x0 plus h, x0 plus 2h. So notice in this case, I'm using points only to the right of x0. So I'm not using points to the left. I'm not using like x0 minus h. And sometimes I have to do it that way, because what if I don't have values of f to the left of x0? Like suppose I have a vector of values of f, and this x0 is the left boundary point. Then if I want a derivative, I have to use this data. Okay, so here's what I do. I go ahead and take Taylor expansions. At this point, I don't really know how far I need to go. Well, that's something that you can figure out. Better to go too far, but not far enough. But what's going to happen is we have three values. I need to find coefficients for combining these values. Three coefficients. I need to set up a system of three equations and three unknowns. And we'll see what those equations are in a moment. So here's the form of my approximation. I have a linear combination of f of x0, f of x0 plus h, f of x0 plus 2h. And I divide by h, and that's just for convenience. I don't absolutely have to do this, but at least this way, what will happen is the coefficients c0, c1, and c2 will be just numbers. They'll be independent of h by doing it that way. And then I'm going to have some error. So the Taylor expansion will help me figure out what this error is. Okay. So what I do here is I take my Taylor expansions, f of x0 plus h, x0 plus 2h, and I substitute them here and here. So that leads to this big monstrosity here and here. Then I regroup. So I take all the terms involving just plain old f of x0 and gather them together, all the terms involving f prime, and then, so I group by order of derivatives. So notice I have all the f terms here, f prime, f double prime, f triple prime, and so on. Okay. Now, so since I have three coefficients, I have three equations that can determine them. So I don't want f of x0 in my expression. I want f prime. So this should be 0. Since I want f prime, this should be 1. Now notice here I had a 1 over h out front, but notice all the f prime terms are multiplied by h, so they cancel. So here I just have the coefficients. So this should be equal to 1. Here I don't want that double prime at all, so this should be 0. Now, I would like for this to be 0 also, but I can't do that. That's an overdetermined system. So I can impose conditions on these terms here. So the first terms, however many coefficients you have, you can specify values for that many terms. This will help me get my error term. So I can use these three conditions to figure out C0, C1, C2. Substitute those values in here, and that will give my leading error term. So now I have this system of equations that comes from what I described earlier. So now I can just go ahead and solve this. And I've carried it out down here. So I use a third equation to eliminate C1. So then I can use a second equation to get a value for C2. So here are my coefficients. So C2 is minus 1/2, C1 is equal to 2, and then C0 is equal to minus 3/2. So then what I do is, okay, I go back to where I was. So this is gone. This is now just f prime. And then this is gone. Now, I only have f prime on the left side, and I have f prime here. All of this, therefore, has to be 0. Now, I have values for C1 and C2 now, so I can substitute those in here. So I go ahead and do that, and what I get is minus h squared over 3 f triple prime. And then plus this plus error equals 0. So what I can do now is solve this equation for the error. So whatever coefficient I get from this, the sign will change. So this is the error. H squared over 3 f triple prime of x naught plus additional terms that are order h cubed. So more precisely, I have my approximation here, but really I want to write this in a way that includes the error term. So plus h squared over 3 f plus order h cubed. Or I can also write it this way. I can remove this part, and I have the unknown point here. All right, so whatever points I use to create the approximation, C is an unknown point that lies in an interval containing those points. All right. All right, so this is how you use Taylor expansion to come up with approximation derivative and error term. Now, notice I have C1 is equal to 2, but notice the other coefficients, I have minus 1/2 and minus 3/2. I want a common denominator of 2h. So that's why I have a 4 up here. Reflecting a value of C1 being equal to 2. Any questions about what happened in this example? Okay. Now, I want to point out some patterns though. Look at the system of equations. Notice the first row, we have sum of all the coefficients must be 0. And that's going to be true in general. However many coefficients you have, they must sum to 0. The reason why is, suppose the function f is constant. Then, so then what would happen is, this approximation would just be the sum of all the coefficients times that constant. But the derivative of a constant function is 0. We need to make sure that if f is a constant, the approximate derivative ought to be 0. That's why the sum of the coefficients has to be 0. And then look what happens here. For C2, we have coefficients of 1, 2, 4. Here we have coefficients for C1, 1, 1, 1. And then here we have 1, and then 0, and 0. So in general, as you go down the rows, you have powers of your multiples of h. Like here we have 0 raised to powers, 1 raised to powers, 2 raised to powers, and so on. So the matrix of your system of equations has a nice structure. Also, for a first derivative, your right-hand side values will always be 0, except for the second one, which is 1. And the reason why it's the second one is because from your Taylor expansion, the second term is what involves f prime, which is what you're trying to get. So now what I'll do is I can describe a general approach for approximating derivatives, at least first derivative. Then I'll talk about higher order derivatives after that. And then I'll do another example that's a little more elaborate so you can see this process carried out. So more generally, we have equally spaced points surrounding x naught that could be on either side of x naught. That's why I have indices that can be negative or positive. So I can have any number of points to the left of x naught and to the right of x naught. So I have coefficients multiplying these values of f, and then I always have a 1 over h out front. Now this is for first derivative. If it was like second derivative, I'd have a 1 over h squared factor, and so on. Now, when you carry out Taylor expansions of these around x naught, and then you group terms by the order of derivative, and then you set coefficients of f prime equal to 1, all of our coefficients equal to 0, what you always get is this system of linear equations. Yeah, so you have a system of linear equations to solve, and now I can describe the components of that system. So the right-hand side B is always a vector of all zeros, except the second element is 1. Here are your coefficients of your your finite difference formula. And then the entries of a matrix all have this form. So the base depends on the the base depends on the indices of multiples of h. So the indices of the points that are used here. The exponents depend on the row. So 0 for the first row, 1 for the second row, and so on. So then you can form this matrix and this right-hand side, and then you can solve a system in Matlab using a backslash. And then get your coefficients. And then you can include those in here, and then you're dividing by h. And then from the terms in Taylor expansion that do not cancel, you can get the error term. And then this is the order of accuracy of your finite difference formula. Depending on how many points you use to the left and right. So versus in the previous example, we used 2 points to the right of x naught, so k was equal to 2. And we did not have any points to the left of x naught, so j was equal to 0. So the order of accuracy was 2. Okay. So what I'll do now is carry out another example. So all these formulas that we get are called finite difference formulas. All right, now what we're looking for is f prime equal to, so we have 1 over h, and sum minus 2 to 2 okay. So we're going to use 2 points to the left of x naught and 2 points to the right of x naught. Plus some error. So we want to figure out what the error term is too. Okay. Now, so I can show you how you can get these coefficients in a method that, while it's based on Taylor expansion that I just showed you, I don't actually have to carry out the Taylor expansion. What I can do is just form this system of equations that would come from Taylor expansion. Okay. Okay. All right, so now I'll write out the entire system. So we have 5 coefficients, so we have a 5 by 5 matrix. All right, so the right-hand side is the easiest part. There's a vector of 0, 1, 0, 0, 0. So the second element is 1, all of them are 0. My solution, I'll have a coefficient c to the minus 2, c minus to the minus 1, 0, c1, c2. So, oh, minus. Yeah, the minus was not typed for some reason. Okay, so this is for f of x naught minus 2h, f of x naught minus h, x naught plus h, x naught plus 2h. Okay. Now, for my matrix, what I can do is plus 2 raised to the 0, minus 1 raised to the 0, 0 to 0, 1, 2 to the 0. Oh, something went wrong here. Okay, so the indices, minus 2 to 2. Whatever indices I have here, first row is those raised to the 0 power, and then for subsequent rows, raised to the same indices, raised to higher powers. Oh, something went wrong here. Try again. Okay, so now I just got to fix all these. Okay. Now, obviously, this can be simplified quite a bit. Oh wait, I need to do these two. Hang on. Okay, got them all. But I want you to see the pattern of where all the entries come from. Okay, so yeah, so certainly, like for the third column, we have a 1 in the first position, and then zeros after that. The first row will be all 1s, and you work on these powers from there. So, and then what I can also show you, right, so what will happen is, here we have, this comes from terms in the Taylor expansion up to order h to the 4th, and involving the 4th derivative of f. So the next term in the Taylor expansion will lead to the error term. So what we're going to get is h to the, okay. Well, I want to show you what this is based on. It comes from, so same idea as what we had here. So notice we have third derivative. Now third derivative is normally associated with h cubed over 6. But we have this 1 over h out front, which is why this is only h squared out here. So similarly, the h to the 4th over 5 factorial times the 5th derivative at an unknown point. And then what we're going to have is minus 2 to the 5th times the corresponding coefficient. Oh, it should be to the 5th power, not the 4th. Ah, dang it. Okay. All these powers should be 5th. Okay. Plus error. Is equal to 0. So really the error is going to be minus all of this. Okay. So once we have these coefficients from solving this system of equations, we can substitute those coefficients in here and get the leading error term. Okay. So the general error term is going to be, so when using general indices starting from j points to the left of x naught and k points to the right of x naught is going to be h to the n over, all right, so I need to give some notation. I let n be equal to j plus k. All right, so h to the n over n plus 1 factorial times a sum. Then we have I raised to the n plus first power times ci. And then a minus, because this plus the error is equal to 0. Okay. All right, so that's how you can work it out in general. Okay. So what I can do now is I can go ahead and solve the system. Now, what I did is well, first, any questions up to this point before I actually bring in the numbers? So here are the coefficients I get. So I'm sort of cheating here from where I went to Matlab earlier. It's equal to 112. 1 is equal to minus 8 twelfths, minus 2/3. I want to have a common denominator. 0 is equal to 0. When it's symmetric, the coefficient of f of x naught tends to be 0. C1 is equal to 8 twelfths, and so it's nice and symmetric. Well, yeah. Okay. Okay, that's all of them. So here's our approximation. F prime equal to, okay, so H, so I have f of x naught minus 2h minus 8 plus 8 f of x naught plus h minus x naught plus 2h. Okay, yep. And then when the coefficients are substituted in here, what I got, what you get from all this is minus 4. And then 5 factorial is 120. But then you get this minus sign in here. So the area that you get is plus h to the 4th over 30, fifth derivative at an unknown point. And sure enough, okay. Oh, I don't have this shared, but I will in a second. Okay. I'm going to temporarily unshare and reshare. Okay. So here it is. So the same 5-point formula that I just showed you. And sure enough, that's the error term picture on point over 30 times h to the 4th. All right. Now, okay. And I'm going to show you what I did in Matlab. Okay. So I knew that the first row would be all ones. So then I have the vector of indices minus 2 to 2 raised to powers 1, 2, 3, and 4 to fill out the matrix. And notice I use dot up arrow because I'm taking a vector and I'm exponentiating each element of the vector. So I needed a dot for that. And then for my right-hand side, vector of all zeros, I get up to 1 in the second position. Solve the system using backslash. And that gives me my coefficients in order. So minus 2, minus 1, 0, 1, 2. And to get the error term, I took the same vector of indices, raised one to the 5th power, and then, now this is a row vector, and C is a column vector. If I multiply a row vector by a column vector in that order, it's a dot product. So this is equivalent to this sum right here. Okay. And that gives me a value of minus 4, which is what goes in here. But then I have h to the 4th over 5 factorial, and that gives me this error term. H to the 4th over 30 times the 5th derivative. Oh, actually, I need to include that. Also, direct by the coefficient. Ah, stop it. Why did that happen?
All right, AC/DC.
Yeah. That sounded where. Okay, m plus first derivative at unknown.
Just rocking out at the coast.
Okay. Okay. Okay, yeah, I do have it here. Okay. So that's how you can use Taylor expansion around x naught to come up with these finite difference formulas and figure out what the order of accuracy is and the constant of the error term. All right. So, questions about any of that?
Professor, so here we use the convention that 0 to the 0 power is 1.
Yes.
And I don't know how we get the matrix A and why the error is the combination of the coefficient and of their dot product.
Okay.
Maybe we look back to the matrix first.
Well,
I don't know how.
okay. Well, I think I can answer both questions at once because they actually come from the same thing.
Okay.
It might be easier to see from the first example I did involving Taylor expansion, because if you notice here, like here I had f of x naught plus h and then x naught plus 2h. So right here, h, 2h, h squared, and then, oh, you know what? I'm going to rewrite this so it's easier to see. If I have, no, not that. Okay. Even though all this is correct, it's not intuitive. 1/2, and then 2h squared. And then here I have 1/6, 2h cubed, and so on. And I think when I'm combining all the terms, corresponding to, right. Now, as long as I keep these factorials set aside, that's why I have them pulled out here and here. If you look what we have here, we have, for C2 is always multiplied by the power of 2, because it's x naught plus 2h. And you can see that reflected in this system of equations. Yeah, and here we have powers of 0, but here 0 to 0 being 1, and then it really is 0 after that. Powers of 1, powers of 2. Yes?
That would be only in this case because we have x plus 2h, right?
Yeah, but x naught plus 2h for this point, and then x naught plus h gives rise to these.
Okay.
And then x
And
naught
powers
itself.
of 2 goes on the third derivative column.
Or the column corresponding to x naught plus 2h, which in this case is the third column. But for this example, fifth column.
So, just for instance, if we had x naught minus h, x naught, and x naught plus h, in that case we would have powers of respective coefficients?
Yeah. Yeah, so if you're using, like, for instance, okay, x naught minus h, x naught, and x naught plus h, I'd have a 3x3 matrix, powers of -1 in the first column, powers of 0 in the second column, powers of 1 in the third column. I solve for coefficients. The coefficient of x naught happens to be 0 in that case. And then I get plus or minus 1/2. Or the other, that's a center difference.
So how many points we have? We have how many n by n matrices A for A?
Yes, how many points you're using, like in this range of indices,
Yes.
is the size of the matrix. Now, and then, once you've specified this system that determines these coefficients uniquely, the next row of the matrix leads to the error term. Because here we have a matrix vector product equaling 0 or 1 for these terms. So now, if you made this matrix one row more, you'd have no f of x naught terms. F prime of x naught would be coefficient of 1. These terms would go away. What you have down here, the next element below this, is minus the error. And the only reason it's minus the error is because of our notational convention for expressing these approximations. F prime equals the approximation plus the error. So the pattern you see in making a matrix continues down here for error. And that makes sense, as you can see from the Taylor expansion, I'm grouping all these terms. These three determine C0, C1, C2. Here's the next term. it won't help me get these coefficients, but once I have them, this gives me the error. And it follows the same pattern.
I'm not quite clear on why it's minus error.
Oh, because everything we have over here has to equal f prime.
Okay.
So once f prime is accounted for, all of this has to be 0.
So just to cancel it out, we
Yes.
take negative.
Yes. And again, that's because these rules are written this way: exact equals approximation plus error. If I had convention the other way, where the error was over here, I would not negate.
Because then it wouldn't be counted.
Right, yes.
Because it is also can be generalized to if we approximate third derivative or fourth derivative, we just change b, vector b.
Yes, that's the next thing I need to talk about.
Okay.
Actually, before I do though, so I gave you a couple examples, but I really should mention certain other, the most popular finite difference schemes for first derivative. So here's the simplest one of all. You would recognize this from the definition of derivative. That's called a forward difference. And if you follow the same procedure I described for getting the error, this is the error. So it's only first order accurate. So it's not a great approximation, but it's a very simple one. So that's forward difference. And then if I take h and replace it with minus h throughout, then I get the backward difference. And that has the same error except for the opposite sign. And then what I can do, but notice these error terms, because they are the same except opposite sign, of course the unknown point is different. If I average these two, it has the effect of canceling out the leading error term. So now I have the, here it is, the centered difference, and this came up in the homework, one of the early homeworks.
Yes.
Yeah, and because the leading error term is canceled, this is second order accurate.
Oh yeah, it's in homework too.
Yeah, yeah. So the same approach to Taylor expansion is all of these, but it's a lot simpler in these cases because they're only using a few points. Okay, and then other rules. Okay, this one is one I worked out. My first example. Okay, all right. Yes, I want to make you aware of those rules. And the thing is, you would think that among those simple rules, that people would always use standard difference because it's second order accurate, whereas forward and backward difference are only first order accurate. But what if you want to derivative x naught and you don't have f of x naught plus h? If you don't have any data there, you can't use a standard difference. You'd have to use either a backward difference or some higher order scheme that is a backward differentiation rule. So you have to take into account what data is actually available to you in selecting which approximation you use. Also, when it comes to error, people focus on the power of h. You know, is it a second order accurate scheme? Is it fourth order accurate? But you cannot ignore the derivative that's involved. Because the higher the order of accuracy of the approximation, the higher the derivative involved. What if f, you only want f prime. What if f is not psi times differentiable? Then this error, even though it's multiplied by h to the fourth, can still be very large. So you have to be careful about that. So that's why a lot of times people prefer to use low order schemes if the functions that you're working with are not very smooth. Because that way, that can lead to a more accurate approximation than if they use a higher order accurate method that would depend on a higher order derivative that might not exist. So,
But how about we interpolate the data first and just differentiate the interpolation polynomial?
so that's actually the approach I'll talk about on Thursday.
Yeah, so does it use the same result?
For these cases of equal spacing, yes.
Okay.
Now, that actually, both approaches can be used if you have non-equally spaced points.
Yes.
But if you want a derivative at a large number of points, best to use equal spacing because then you can use the same rule for each one. But the problem is, if you're using a large number of points, and what have we seen with equally spaced points in high degree interpolation? That's Runge's example. So you're differentiating a polynomial exactly, but the polynomial is not a good approximation of f.
So,
Therefore, a derivative of f will not be a good approximation.
For
of
data.
the derivative.
Yeah, so, and actually, for some problems, we do use Chebyshev differentiation matrices that that are a lot more complicated than these.
That's why we just differentiate the Chebyshev polynomial.
Yes, that is done for certain problems. The difficulty there is instead of using points just near x naught, you're using a large number of points, and it can be very accurate, but it's less efficient. So so that's so it is a double-edged sword. The numerical differentiation is it seems like a simple thing to work out, but there are a lot of difficulties that can come about. Okay. Yeah, I do need to talk about higher order derivatives. Okay. Okay. So. Okay, so let's suppose we have, the p derivative at x naught. So that's going to be equal to 1 over h to the p. And same kind of coefficients. Ci f of x naught plus ih plus error. Okay. So we get to solve the system. AC is equal to, I'll call the right hand side BP, where, whoops. Okay. BP has all entries 0 except the p plus first entry is equal to p factorial. And the reason for that is if you look at the Taylor expansion from a first example, even though that was the first derivative, like here, suppose we actually wanted a second derivative. So we would want this term to go away, this term to go away, and this needs to be equal to 2 to cancel with the 2 out here. Okay. And then because we have a 1 over h squared out front, then this h would go away also. So that's what works to change the right-hand side in that case. So the matrix will be exactly the same. Okay. What that means is you need to make sure to have enough equations here to uniquely determine the coefficients and actually get a valid approximation of whatever derivative you're after. So for instance, if you want the second derivative, you've got to use at least 3 points, or you won't get an approximation at all. Okay. And then as far as the error is concerned, okay, that will be similar. And be careful about this. I haven't actually worked this out before. I'm going to do is copy a previous one and then adjust it. All right, so it's going to be h to the n plus 1 minus p is the order of accuracy that you would get. Where, as before, n is equal to j plus k. Okay, so something I need to think about this for a second, because as an example, like suppose I said j and k both equal to 1, and I want the second derivative. So that's going to be a center difference approximation. This would suggest first order accuracy, but the thing that I have to be careful about is symmetry. So as an example, I'm going to let p equal 2, j equal 1, k equal 1. So, I want the second derivative. Squared. And it's going to use 3 points. So c minus 1, f of x naught minus h, plus c naught, f x naught plus c1, f of x naught plus 2h. Okay. Plus error. Okay. So now I can set up the system of equations. So this is going to be a 3 by 3. Okay. So I'm going to have ones in the first row. And then I'm going to have, okay, so everything to the first power in the second row. And then the second power in the third row. Okay. These are my coefficients. All right, so c minus 1, 0, c1. All right, and then my right-hand side. Zero, 0, 2. Okay. All right, so now what I can do, if I go ahead and put the system into Matlab, all right, so 1, 1, 0, 1, 1, 0, 1, 0, 0, 2. Okay, and these are coefficients that I would expect. So now, okay. Now my approximation is f double prime x naught. This is the centered difference. Okay. Sorry?
Is it supposed to be x plus 2h in the third term?
Wait, where?
In the third
Oh, that should be. Okay, whoops. Not sure how it happened. Okay, f of minus h. X naught plus h. Okay, so this is my approximation. Plus error. Okay. Any questions up to this point before I look at the error term? So if I were to evaluate this, because I'm going to make a copy of that. Okay, so we have j and k both equal to 1, and n is equal to j plus k. So that would be equal to 2 in this case. P is equal to 2. So that would suggest that it's only order h. Actually, generally, if you use a minimum number of points, you're going to get an approximation that's first order accurate. And then we have 3 factorial down here. And then my sum, okay, so I cubed, yeah, and then I have the third derivative at triple prime at an unknown point. But let's see what that turns out to be. So h over 6. And what I get is, so minus 1 cubed, that's minus 1, times c sub minus 1, which is 1, plus 0 cubed times minus 2, plus 1 cubed times 1. What happens here? 0. All right, that's the symmetry at work. So no problem. Go to the next row. So, all right, so 2 minus p. And then I'll have n plus 2 factorial. Okay, and the coefficients are the same, and plus second derivative. All right, let's see what that turns out to be. I know what the answer is supposed to be, so let's see if it actually works out that way. Okay, so n is equal to 2, so 4 minus 2, so h squared over 4 factorial. And then we have, all right, I to the 4th, ci times, this was, make sure I have this, n plus 1, so n plus 4th derivative. Okay, so this sum will turn out to be, so minus h 4th over 20. H squared rather over 24 times minus 1 to the 4th times coefficient. All right, so these don't cancel out, they add together, and we get minus h squared over 12. Oh, I forgot the derivative. Okay. So it's the first, so we keep going through rows, like subsequent rows of the matrix until we get something that's non-zero. That is where the error term comes from in the most general case. Now, okay, I show you, yep, and sure enough, there it is. So, wow, it worked out, minus h squared over 12. So that's kind of shocking when you see it happen. Because none of this was planned, I assure you. Okay. All right. All right, and it's because of symmetry of approximation that sometimes this can happen. Okay, so it's something to be mindful of. Okay. Some questions about what happened here working out these finite difference formulas or their errors.
Yes, sir. So the matrix A actually is the transpose of random matrix, right?
Oh,
Is there any more
Yeah.
efficient method to compute the linear system? Yeah, I just noticed it is the transpose of the random matrix.
Yeah. Well, I've seen the general matrix. Sometimes, well, I guess sometimes the order of columns is different, but yeah, it's a transpose.
Yeah.
Oh, sometimes I've seen. Well, okay. Now I think about it. Yeah. Okay. Right. But yeah, that's an unfortunate choice of matrix because I've seen the polynomial interpolation.
Yeah.
it has its problems, but because the other approach that I'm going to show you on Thursday, involving Lagrange polynomials, I mean that can be quite a pain also. Because really what you're doing is you're multiplying the inverse of transpose of Van der Waals matrix times a multiple of a column of identity. So it's almost like you nice to have a formula for the inverse of a Van der Waals matrix. Right. But I don't know if any such formula exists. But I feel like one can be worked out. Maybe there is one out there. I just don't know. Okay. Other questions or homework questions? We have time for that too.
For these approximations, do we need to, would f of x be known, or would we just have a set of points and then we're approximating f of x first and then approximating the derivative?
What I've seen in applications is that you only have the values of f at selected points. Like it's defined on a grid. Like for example, if you're solving, for example, a system of ODEs or a PDE, and so what your computed solution is nothing more than a vector of values of a solution at equally spaced points. So unfortunately, you're not able to evaluate f at any point one.
Could we see an example just to see it in application?
Oh, okay. Let's see. All right. So in one dimension, Poisson's equation, which in one dimension is minus u double prime of x is equal to some given function f of x. So if you're given values of f at selected grid points, okay, I can define an interval here. On the interval, say 0 to 1. I've actually been doing this in one of my other classes, Math 7.1. So a given f of xi, where the xi are equally spaced points in 0, 1. Xi is equal to I, H. H is a spacing. So like n, capital N is the total number of grid points you have. And this is the spacing between them. So, okay. And we assume boundary conditions. We assume u is equal to 0 on the boundary. Then we have the following. The ODE, or Poisson's equation, talks about the following. Okay. Hold on. Grid points xi. Alright. So we have minus, and then I use the standard difference I just showed you for the second derivative. a parenthesis here. Plus uxi plus 1, okay, is equal to f. Okay,
So just to be clear, is it xi minus 1 or xi minus 1?
oh, I minus 1 is the subscript. Because this is equal to xi minus h, and here plus h. So I'm representing a solution on a grid of equally spaced points. So to approximate the ODE at a given point, I use points to the left and right. And this approximation has an error of order h squared, because this is a second order accurate. So what I have here, I have n of these equations in unknowns. And linear equations. I'll call them ui, which is an approximation of uxi, just for convenience. So I can write out what the whole system of equations looks like. So I have minus 1 over h squared. Okay, I'll fill out the matrix in a little bit. 1, 2. M. Okay, equals f. So then I have values of f on the right side. So in the matrix, what I'll have here are the coefficients. I've already factored out the minus 1 over h squared, so I'll have coefficients 1, minus 2, and 1. So I'm going to have minus 2's down the diagonal. Oh, whoops. Okay. So minus 2, 1. We'll kind of fill in the matrix. Okay. So we're going to have minus 2's down the diagonal. I think I have 1, 2, 3. Okay. And then 1's above and below the main diagonal. Okay. Oops. Oh, we got some. That slash is getting away. Okay. All right. So the coefficients come directly from the coefficients of the finite difference formula. So because I'm approximating u double prime at xi, the value of u at xi is multiplied by minus 2. That's why these are on the diagonal. Here, this is the point directly to the right, so these 1's go directly to the right. Here I have a coefficient of 1 for a point directly to the left, so these 1's go directly to the left. This is called a differentiation matrix. I multiply this matrix by a vector of values, and that approximates the appropriate derivative. So here we get minus u double prime, approximately anyway, is equal to f. So this example how these finite difference formulas lead to solving like differential equations by setting up systems like this one to solve. I'm not sure if that.
Not completely,
Oh, okay.
but.
Sorry, what?
Not completely.
Oh, what else? Tell me.
I don't know how to explain.
Okay, can you repeat your original question, please?
No, I just wanted to see it in application, that's all. I said initially that it didn't absorb completely, that's all.
Oh, okay.
I need some time.
Okay. All right. We still have a little more time for questions of any kind. All more questions too? Everybody's brain fried? Okay. I'm happy to call it good too. All right. Well, we'll continue differentiation on Thursday.